Okay, uh, let's start. Hello, everyone. Nice to see you again. Today we have the third talk in the colloquium series this year. And first of all, I would like to acknowledge the traditional owners of the Australian land and pay my respect to the elders, past and present. Today, I am happy to present Ana Maria Rey, who is professor at the University of Colorado and Gila, as well as a fellow in the National Institute of Standards and Technology. So Gila started in 60s as a joint institute for the laboratory in astrophysics, but evolved in the leading research center with very broad perspective. And Ana is one of the leaders and pioneers in the cold atomic physics, including quantum simulations, orbital magnetism, topological matter, and beyond. Ana Maria made her PhD degree in the University of Maryland in 2004. And after two postdoctoral appointments in the National Institute of Standards and Technology, NIST, and the Institute of Theoretical Atomic, Molecular, and Optical Physics at Harvard, she joined University of Colorado in Gila as a faculty in 2008. Ana Maria has a number of fellowships and prizes. She is a fellow of American Physical Society, has received Blavatnik National Award, Alexander Cruikshank Award in Atomic Physics, and Presidential Early Career Award for the Scientists and Engineers, and a few more. So before we start, Anna has told us that she encouraged questions and happy to be interrupted. And Anna, feel free to start and we will enjoy the talk.
Okay, thank you very much, Dimitri, for the invitation to speak today. It's a great pleasure for me. So what I want to do today is to describe the fascinating idea of how atoms and light can be used to create atomic clocks. They're the most precise timekeepers ever imagined. I think together we are going to take a look at the inner workings of atomic clocks, and hopefully I can convince you that atomic clocks are fascinating and important since they are well, not only keeping time, but help us to unravel big mysteries about the quantum world, and hopefully will be used for building the next generation of quantum technologies. So before I start my talk, I want to acknowledge my collaborators and the actual clockmaker, the experimental group that does the clock is John G. And I'm just, you can see here, his fantastic group of postdocs and graduate students. They are the ones that took the data here. And of course, I want to acknowledge my theory collaborators. In particular, I want to acknowledge Anjun Ku. He was the person who did a lot of the calculations that I'm going to present today. All right, so very briefly, just to for everybody and for general basis, so just want to explain what we mean by ultracold atoms. So of course, the temperature is a measurement of the average kinetic energy of the gas of the atoms. And if we are at room temperature, the atoms are moving very fast, like about the speed of sound, 300 meters per second. And therefore, if we want to control and manipulate these atoms, it's going to be very difficult. And if you start to think about what are the coldest temperatures that you can have naturally in the universe, then you might think, well, yes, maybe the temperature of the outer space. And if you think there is a few kelvins, and if we do the corresponding temperature, for example, of a gas, this about 4 Kelvin is the temperature where helium condenses, but still at this temperature, the atoms in helium are moving very fast, like 90 meters per second. So one of the biggest achievements that we have done in atomic physics was the possibility to cool down gases that consist of 10 to the 4, 10 to the 6 atoms to temperatures very low, between 10 to 100 nanokelvins, and very dilute. So we are talking about the gases that are 5 orders of magnitudes the density of air. And at these conditions, the atoms move really slow at the order of centimeters per second, and therefore it allows us to actually manipulate them and cool them down. This has been the work of many scientists, and the work has been recognized with two different Nobel Prizes in 1997 First, it was recognized to Steve Chuff, Cohen Tanuji, and Bill Phillips for using lasers to cool down the atoms using light at two temperatures of the order of microkelvin temperatures. And then it was a follow-up by Eric Cornell, Wolfram Ketterle, and Carl Wyman, when they were able to actually use evaporative ideas, so like atoms escape from hot atoms escape from a cup of coffee. Same for atoms, they were able to achieve much lower temperatures of the order of hundreds of nanokelvin and create for the first time a Bose-Einstein condensate. So, of course, one of the questions that we might ask ourselves is what we can do with these ultra cold systems that are fully controllables. And one of the most exciting directions that I can think about is to use them as a tool to explore the quantum world. And in particular, so for example, one of the open exciting opportunities that they offer is the capability to simulate the behavior of electrons in solids, but in more controllable conditions, and therefore allow us to build new type of synthetic materials with capabilities that could outperform what we find in nature, and try to, for example, understand them and use them for better technological applications. Of course, they offer the dream of trying to build the most precise computers. I mean, this fascinating idea of a quantum computer that kind of performs even the best supercomputers that we can imagine thanks to the quantum advantage. Also, the idea that is they offer a tool for exploring fundamental physics and perhaps answer one of the biggest mysteries that we have currently in quantum science, that is trying to connect the behavior of the microscopic world that is ruled by quantum mechanics with the macroscopic world, like astrophysical objects that is ruled by general relativity, trying to see how we can, for example, connect these two extremes. And finally, the idea of using these systems for creating ultra-precise sensors with capabilities that we cannot get with classical systems, but actually use the laws of quantum mechanics to actually improve what we can do, or we have done so far. So I think cold atoms, atomic systems, open a path to answer all of these questions. But in particular today, I want to take the opportunity to talk about atomic clocks as a specific atomic systems that actually have that offer very powerful opportunities into all these interesting directions, and I try to emphasize a little bit of that. So I want to start very basic. So what is a clock? Well, a clock, we know, is something that ticks in a regular and repeated manner, and we use to measure time. And as any clock, even the simplest basic clock, the pendulum clock, consists in two parts: an oscillator, that is what ticks, and the counter, that is what counts the oscillations and we use to measure time. Then atomic clocks are exactly the same. They also have two elements: the oscillator, what ticks, that is an electromagnetic wave, and what records the oscillations, the counter, in this case is atoms. So what happens is that the oscillations, for example, for the case of atomic clocks, in some cases can be so fast that even electronics cannot measure, but instead the atoms are the ones that allow us to track these very fast oscillations. Why atomic clocks? Well, because they provide an unrivaled definition of the seconds based on principles of quantum mechanics. The fact that the energy of the atoms are quantized and are the same here in China, so the clock that we build is going to be universal. So in fact, since 1967, the definition of the second is based on the energy splitting of two hyperfine levels in the cesium atom. Basically, the second is defined by about, I mean, you can see the number here, that is about 9 billion periods of radiations in this associated with this transition in cesium. The first clock was created in 1955 back by Essen and Perry, but of course clock has progressed at a very exponential rate and done a very important performance. But something that I want to emphasize is that even though we use cesium for defining the standards, nevertheless, who currently cesium is not the best in the world. And why is that? Well, the answer is simple. If I give you these two rulers, ruler A and ruler B, and I ask you which ruler is more precise, well, you are going to immediately say, well, of course, more ticks, higher resolution. And it's the same for clocks. So in the case of the cesium clock, what happens is the energy splitting is of the order of microwave transition, and therefore the oscillations are much slower. But the idea is that we can generate clocks that is called optical clocks, where the energy splitting is much larger, faster, like the order of 10 to the 4, 10 to the 14, 10 to the 15 hertz. Then in that case we have much faster ticker, so it can be a 4 or 5 order of magnitude faster than microwaves, and therefore we can enjoy more resolution. And this is the story of the clocks that I'm going to tell you today. So in that case, in order, as I mentioned, we have the oscillator, that is in this case a laser. We have the atoms that are going to, the ones that are going to count the oscillations, and basically we need to do a feedback cycle that is going to try to lock the frequency of my laser to the frequency of the energy splitting of the atoms. And well, now for the case of the optical clocks, the atoms that we use are those in the second column of the periodic table, or others with similar atomic structure like ytterbium. For example, here, these atoms are characterized by having two outer electrons, well, this gives a unique atomic properties, as I will show. And in particular, for this talk, we're going to focus in strontium, that is the atom that we use at GILA. Also, for this talk, I'm going to focus on the fermionic isotopes that, in addition, have a nuclear spin I that is larger than 0. So, besides two internal states that we are going to measure the clock transition, there are going to be an additional set of nuclear spin levels that are going to let me use more degree of freedoms, as we will see. In the case of strontium, I can be as large as 9.5, so we have 10 additional levels per manifold. Okay, so why alkaline atoms? Because they have a ground electronic state with J equal to 0, and also they have an excited state that is also J equal to 0. The ground state is a singlet, and the excited state is a triplet. So this transition is an optical transition that is both spin and dipole forbidden. It's slightly allowed because we have a hyperfine structure in the excited state, because of the nuclear spin, but it's really narrow. Still, the transition is the order of the width is a line width of the order of millihertz. That means that this state has a lifetime that can exceed 100 seconds. So if you try to imagine this atom in terms of a classical pendulum, and we use a quality factor that is the ratio between the ticking rate to the damping rate, it can be larger than 10 to the 17. So it corresponds to a pendulum that it will swing, when set, it will swing for the entire edge of the universe. So that's the quality of the atom that we have. Well, of course, it's not only the quality of the atoms, but we have to develop ultra-stable lasers that are going to take advantage of this very narrow transition. And this has been mastered in Jun's J group at GILA. He have been developed ultra-stable cavities that are available, allow him to create lasers that have coherence time for more than 10 seconds. And finally, we have to make sure that these atoms, the atoms that we use for the clock, are free of fundamental systematics. And if you think about what are the most important systematics in a clock, you can say of motion could be really bad, because of course Doppler shift will make the frequency splitting that depends on the velocity of the atoms, and that will be bad. So that's why we trap the atoms actually in an optical lattice that is a periodic potential that is generated by interfering laser beams. So these are different pancakes of the lattice. It's a 1D lattice, such that they create an interference pattern. Atoms get trapped in each of these pancakes, and they cannot move from one lattice side to the other. We want initially to make it very tight, So the motion along the propagation of the laser direction is suppressed. So we remove Doppler shifts, and to avoid the issue that the lasers that confine the atoms generate energy shifts because the atoms feel different potential, then what they use is what is called magic wavelengths, where the trapping potential for the ground and the excited state is identical, and therefore we remove any type of systematics from the trapping beams. So we avoid Doppler shift or star shift or recoils, and this is what set the capability to generate these very precise clocks. So now, respect to the locking protocol, in order how we lock the laser to the atomic transition, one of the protocols that we use is Ramsey spectroscopy that was proposed by the Nobel Prize Norm Ramsey back in 1989. And the basic idea is if I have my two levels, the ground and the excited state, and I want to interrogate this with a laser, and I want to flock the frequency of my laser to the frequency of the atomic transition. So what I do is I prepare my atoms in the ground state, and then I apply a pulse. I'm going to define the detuning, that is the difference in the frequency of my laser with respect to the atomic transition. So after the first pulse, I apply a very strong pulse, and what I do is that I create a superposition between the atoms in the ground to an excited state. And depending on how long the pulse area, so the radio frequency of my laser or the time that I do the pulse, then I'm going to rotate the block vector from ground to the excited state, creating the superposition that the excitation fraction is set by this tipping angle theta, and therefore if I have theta equal to pi half, I just have equal superposition of atoms in the ground and excited state. So I do first a pi pulse to create the superposition, and then what I do is that I let the atoms evolve in the dark, but in the rotating frame of the laser, then they're going to accumulate a phase that is determined by this detuning. So there's going to the differential phase between the accumulated by the atoms. It happens during this dark time. The atoms precess like a classical gyroscope, you can see. Think about that, and then what I do is that I want to measure the phase accumulated that give me information of this detuning by applying another pulse that transfer the phase accumulation into population, and I measure the number of atoms in the excited state, and this gives me what is called the Ramsey fringe. When I see these oscillations, that depending on the tuning of the laser, and therefore by looking at the phase, I can of course determine the detuning. And ideally, I want to have these oscillations for a very long time for the precise determination of the detuning, and therefore almost 100% contrast ideally. So so one of the advantage of ultracold atoms is that we can interrogate many atoms at the same time. So here, when I was talking about Sx, was the collective spin of all the atoms. And this is a big gain, because if we have many atoms, we can have a large signal to noise ratio that depends that scales with the square number of the number of atoms. That is good compared, for example, trap ion clocks that operate just with a single ion. So that's great that we can take advantage of the large number of atoms. But then there is a caveat, nevertheless, because my atoms never are not. They do collide, and these collisions, unfortunately, can change the ticking rate of the clock. So it's going to change the detuning that is measured, and of course, the more atoms, the worse the error, because there are more collisions. So collisions are bad for clocks, and the idea that initially we had was trying to take advantage of quantum statistics to suppress these collisions. And that means we want to use fermions in order to do that. And the reason is because, of course, in quantum mechanics, at ultracold temperatures, collisions are also can be quantized in terms of partial waves that are determined by some angular momentum of the relative colliding particles. And so what happens is in the limit of very, very cold temperatures, then the collision is basically determined just by the phase shift. So because of conservation and of energy and probability, the atoms collide, and after the collisions, the only that changes in the wave function is a phase that depends on the collisional channel or the angular momentum. And at ultra-cold temperatures, then the phase shift is universally characterized by a few parameters. The L equal to 0 collisions that are the lowest energy are characterized by an scattering length A, a single parameter, and the next order collisions that are the p-wave collisions with L equal to 1 are characterized by a p-wave volume that is B cube or B. So these are parameters, simple parameters that characterize the properties of the collisions. The important part is that in the case of L equal to 1, you have an additional centrifugal barrier, and therefore the collision costs energy. For the typical strontium atoms, the centrifugal barrier can be as large as 30 microkelvins. So if we have gases of the order of 1 microkelvin, then there will be suppressed. So in our case, for the case of the two internal levels, we are going to have three different scattering volumes: the ground, collision between excited and ground. Well, but the important part is that quantum statistics matters, of course, at ultra-cold temperatures.
Could I interrupt you?
Sure.
I have a question. So if part of your atoms are in excited states and part in the ground state, during the collision, they could switch. Is it will be inelastic?
Yes, so we have there are inelastic process in the excited state. I mean, this is an optical transition, and therefore, typically the number of excitations is conserved because it's a very large energy. So, but unfortunately, as you point out, yes, in the excited state, we can have, remember these are two body collisions, and unfortunately, we do have the situation where two atoms in the excited state can collide and get out of the trap. These are going to be lossy collisions. The other kind of collisions that are the elastic ones that conserve the energy, we can just have a spin flip. Yes, one atom was excited and the other ground, they can flip the states. But the particles are, we have to take into account the quantum statistics, so we define the collisions in terms of triplets or singlet states of the two colliding particles. Yes,
but
so
it could probably result to the dephasing.
Yes, of course, that's why collisions are bad, and that's what we want to cancel them. And that's the reason why for the idea was that if you have fermions, identical fermions cannot collide via the S-wave channel, because two identical fermions cannot have S-wave collisions, and therefore that's why we wanted to use fermions, identical fermions, such that the only allowed channel is the p-wave channel, but is suppressed at microkelvin temperatures because of the large energy barrier. So that was the idea, trying to use fermions to suppress these undesirable collisions.
Okay, so, thank you.
Perfect, thank you. So the experiment started using fermions, and unfortunately, back in 2008, they gave rise to the second largest uncertainty at that time, where the error was of the order of 10 to the 16 minus 16, the uncertainty in the clock. So basically, even though the collisions were, even with the centrifugal barrier, the collisions were very bad, and we needed to understand these interactions to make the clocks better. So this is, the way that we try to understand interactions was trying to take advantage that nevertheless these collisions are weak. So remember that we have an optical lattice that we split the cloud into different pancakes, and there is where the atoms can move in a single pancake. The lattice is very deep, so there is no motion perpendicular, but just motion along in the pancake. And you can visualize the pancake like having a harmonic oscillator. So basically, what happens is that even at the energy levels of the atoms are of course quantized in the harmonic oscillator levels, and the important point is that the energy splitting between these levels is set by the trapping potential, and then is of the order of 500 hertz for the experiments, where the collision energy was very small, less than 1 hertz, and therefore the collisions was not strong enough to make the atoms change the energy levels. These energy mode changing collisions are forbidden, and the only collisions that are relevant at this for this kind of system are just the ones where you just flip the spin between the two colliding atoms. They just change the spin, just spin flips. In this condition, under these conditions, we can think or model the collisions in terms of an spin model where the lattice sites are the energy eigenstates of the system. So atoms are pinned in this energy lattice, and the only thing that they can do is that change the internal levels. So this facilitates the description of the collisions. We can now just assume frozen particles in this energy lattice and write a spin model that describes how the collisions happen during the dynamics. So the other important point is that we are talking about an effective lattice in energy space. So if even though the collisions are contact, atoms bump into each other by bumping at a given position, in momentum space or in energy space, the collisions are all to all because the atoms are in momentum space are delocalized. So when we write the interactions of this spin model in energy space, the interactions are really kind of the all to all because an atom can interact with any other in the ensemble in this momentum basis. And therefore, we can define again a collective spin operator that is the sum of the individual spins. We can write, for example, the total S is the difference in the number of atoms in the excited minus in the ground state. And this is set by the first pulse that we use on the Ramsey spectroscopy and is constant during the dynamics. And therefore, we can write a simplified spin model that actually describes the effect of the p-wave interactions. So it's very basically when you try to write the spin model, you see that the effect of the p-wave interactions consists of two terms. One is ksc squared term, and the other is a term that is sc but depends on the number of atoms. These parameters depends on the p-wave scattering volumes. But the important part is that you can simplify and very simple understand why collisions modify the ticking of the clock if we do a very mean field approximation where we replace this observable sc squared by sc times the mean. And therefore you can see that the delta in the presence of interactions is replaced by two other terms, or you have two other terms that are depending on the inversion that is set by the initial pulse. So basically we see that the modification of the ticking of the clock from collisions depend mostly only on the excitation fraction set by the first pulse. That was the prediction of this very simple model. And this is what they measure, what is the energy shift versus the excitation fraction that they control by the pulse area. The experimental points are with error bars are the measurements, and the solid line is the theory that agrees very well with a ticking of the clock modified by the density that depends on just the excitation fraction. And basically we were able to operate at this point where we were able to cancel the density shift. So we were operating at an excitation fraction that canceled the density shift, and moreover, we were able to use the measurements to determine the scattering volumes that were not known at that time. So as Dimitri pointed out, unfortunately, that was not fully the end of the story because we did have EE inelastic collisions that introduced losses, and we could not interrogate the clock for as much time as we wanted. So there was some limitation on the interrogation time. But nevertheless, by understanding the collisions at that time, back in 2014, we were able to improve the clock, the strontium clock, and make it 1,000 times better than the cesium standards at that time. So now we were able to report a fractional frequency uncertainty of 10 to the minus 18 that corresponds to a clock that neither gain or lose 1 second in some 15 billion years, that is roughly the age of the universe. So that was very exciting. And the story that I'm going to tell you now a little bit is that we have been able to improve the sensitivity 1,000 times more, and we use the sensitivity these for measuring very interesting fundamental quantities, as I'm going to report. So I'm going to tell you the story of how was that accomplished. So, but in parallel, I mean, the one of the exciting opportunities that these clocks are offering is that they offer the possibility to connect precision metrology with many body physics. Why? Because if you if you think about what are the aspects that make strongly correlated materials so difficult to understand, is because there is an intrinsic interplay between orbital spin and charge degrees of freedom in these electronic systems. So the interesting part is that in our strontium atom, we have all of these possibilities together. So we can have an orbital degrees of freedom that are the two clock states. We can have a nuclear degrees of freedom, that I said we have a nuclear spin, and moreover, we can make the atoms behave as charged particles by using lasers and introducing an effective spin orbit coupling. That is what I'm going to tell you a little bit about that. So of course, spin orbit coupling is fundamental in nature. It's the coupling between the electron motion in the spin. It's a relativistic effect and is at the heart of spintronic devices, of topological superconductors, of topological insulators, and when topological insulators are placed close to a superconductor, in principle it can give rise to Majorana fermions that could be a holy grail for quantum information processing. So all just want to say is that spin orbit coupling is interesting and important for many applications. The advantage is that in our atomic clock, we can engineer spin orbit coupling very easy. The only thing that we have to do to engineer spin orbit coupling is to reduce the lattice depth and start to allow the atoms to tunnel from one lattice side to the other. Why? Because what happens is that we are interrogating an optical transition, and the wavelength of the laser that we use to interrogate the transition is very comparable with the lattice spacing of the atoms that we are interrogating. Therefore, the phase of the lasers changes significantly between one lattice side and the next. And this allows the atoms to experience this differential phase and feel them when they tunnel from one lattice side to the next. This introduces a spin orbit coupling on one hand, but the other way to visualize this phase is also trying to understanding as a flux. Basically, the other way that we visualize that is we have the atoms in the ground and in the excited states. This is the tunneling direction, but it can be seen as a ladder because the laser couples the ground to the excited state. So basically, if we have an atom in one lattice side, and then it absorbs a photon from the laser, this is in lattice side 1, it's going to absorb the photon with some phase. Then the atom can tunnel from this n equal to 1 to n equal to 0. Then it can emit a photon to the laser and go from excited to ground. But the phase of the laser is different because it's at different lattice sides. So then it tunnels back, and as it circles around this plaquette, then it's going to accumulate a next phase phi that was imported by the laser, introducing a next flux in the system. So and this occurs naturally. Another way to understand the spin orbit coupling is to imagine the dispersion relation of the atoms in the lattice. So this is the energy versus the quasi-momentum. So in atoms tunneling in the lattice have a dispersion relation that is in the form of a cosinusoidal dispersion relation, where J sets the tunneling rate. And because the atoms feel the same lattice potential in the ground and the excited state, what happens is that the dispersion relation is identical except from at the tuning, because the laser in the rotating frame of the laser, they are detuned by some constant magnitude delta. The point is that when I have an atom from the ground state and absorb a photon from the excited state, the photon, the atom changes its momentum because absorbs a photon from the laser. So the momentum of the atoms is changed from its initial momentum q0 to a different to the momentum that is absorbed from the laser photon. And this, in order to model this, one way that we do that is to, instead of trying to do off diagonal couplings of the laser between the ground and excited state, what we can do is a gauge transformation that still couple the atoms now diagonally, but with the same energy that was transferred. I mean, it couples the states that we were coupling because of the transfer of momentum. That is, an atom in the ground state is now coupled by the laser with an atom with an excited state by QI plus phi. Phi again is the phase that is imparted by the laser. So in other words, what we do is that we have a change in a change in an energy that depends, at the tuning now, that depends on the momentum of the lasers. That's what is called, that's what we have spin orbit coupling. So the tuning between the ground state and the excited state that is connected by absorbing a photon from the laser depends, the energy of these excited states depends on the detune. So basically, if you have, because in this picture, the coupling between the ground and the excited state is diagonal, we can see that in momentum space, the Hamiltonian of non-interacting atoms can be just, or again, considered for a given momentum q as an spin model, a spin system where we have a coupling along the effective magnetic field that couples the atoms between the ground and the excited state by this variable frequency, but actually the tuning now depends on the momentum of the atoms, and therefore it is coupling the spin and the motion. So I have the tuning that depends of my momentum. Okay, so in this picture, there we were able to verify that we have really a spin orbit coupling in a very simple way. So we have the two bands, the ground and the excited space band in this gauge picture. And what happens is that depending of the tuning of the laser, we can change the crossing point of these two bands. So what happens is that because we start with all the atoms in the ground state, and therefore we can interrogate the atoms from the ground to the excited state with a very narrow laser that only transfer the population where the atoms the bands almost touch, where there is on resonance. The other states are not transferred because they are off resonance. We can blow away, and by doing that, we select the atoms with a given window of quasi-momentum. And by changing the tuning of the laser, we can change the window of quasi-momentum we select just by changing at the point, at the crossing point of the dispersion relation. With that, then what happens is that we prepare the atoms in a certain momentum, window of momentum in the excited state, and we then let it evolve with a strong drive. What happens is that they are going to experience Rabi flopping, but at a rate that is going to depend on the momentum that was selected. Because, of course, the orientation of the effective magnetic field in this spin model depends on the momentum. So the atoms are going to have a rate, a Rabi flopping that depends on the momentum. And this is exactly what we saw. This is the number of atoms in the excited state as a function of time. And we see that depend on the window of momentum that we choose, we see different Rabi rates, and therefore verifying that we have, and we are able to see for the spin orbit coupling in the clock. So that was
could I interrupt you?
Yes.
Well, could you educate me? So in solid state physics, we usually assume, so the good approximation that photons don't transfer the momentum. It is neglected.
Yes, that's the difference, because this is an optical transition. If you have a microwave transition, that is different. But in this case, the wave number of my laser is very high.
Yes. How large is the period of the lattice?
Yes, the period of the light is of the order of micrometers.
I see.
And,
Yeah.
and also, so A is the lattice spacing, and K is the wave vector of the laser, and this product can be as large, close to pi, or even larger than pi. So we are transferring a lot of momentum to the atoms when they go from ground to excited state.
Okay. Also, it's I have it's could you uh, so it's clear that you could introduce sigma z term that introduce the energy difference between two levels.
Yes.
Could you say again how the in-plane component of magnetic fields are introduced?
Yes.
If
So, okay.
by
So the point is that let me go back in this picture. So we have a laser that is coupling the ground state with the excited state. Yes. So this is the sigma x coupling. But you can relabel the momentum of the ground state is q0, and then the momentum of the excited state is displaced by the momentum absorbed by the laser. Yes. So basically, you relabel the momentum of the excited state. You just do a gauge transformation that you shift Q. So you see that the energy, we are transferring the atom to this amount, this energy here, and we just now relabel you relabel the momentum of the excited state, and you see that the atoms are transferring the ground to the excited state. But now diagonally, but now the tuning, that is the energy difference between the ground and excited state, is going to depend on the momentum. Is the energy difference, is the energy difference between the dispersion of the excited state, that is cosine QA plus phi, minus the dispersion of the ground state that is not shifted. So it's because you observe a photon when you go to the excited state, then you are going to change the dispersion of the effective dispersion of the excited state and the ground state are different. Does that make sense?
Yeah. Okay. Thank you.
Great. Thank you for the questions. So yes, so we were able to see that there is a spin orbit coupling, and in principle that's interesting for quantum simulation, but it created a problem when we started to look at more dense samples. When you have more dense samples, what happens, as you can imagine, is that when you interrogate the atoms with the laser, the phase changes from one lattice side to the next. So what happens is now that when an atom goes from one side to the other and tunnels, now the atoms are no longer indistinguishable as we were having before, that we're not able to tunnel. Now there is a differential phase that the atoms experience. The atoms become distinguishable, and we open a channel for S-wave collisions between non-identical fermions that are really strong. So in principle, decreasing the lattice depth to avoid undesirable losses, to make the atoms a little bit less dense was bad. But then gravity came to the rescue. What do I mean by that? So we changed it. What we did to prevent that is to change the orientation of the lattice and making along the vertical direction instead of the horizontal direction. That is, we have now a clock where the tunneling between one lattice side to the other cause gravitational energy. That's what we call so this is the ground, this is the excited state, but there is an energy offset between the ground and between the one side and the other. So the eigenstate that describe the motion of a particle in a lattice plus tilt are what is called the Warner-Stark states, that are a superposition of orbitals localized at a given site with a weight that is set by a Bessel function that depends on the ratio between the tunneling and the gravitational energy between one lattice site to the next. That means that our wave functions are not completely delocalized, but the tilt, the gravity, introduce a level of localization that we can explore. So now the atoms are not completely delocalized, and we can control the degree of localization by changing the lattice depth as our under our control. So this is a picture, for example, of these Warninger-Stark ladders at the center of the lattice site as a function of the lattice depth. So for very, very shallow lattice, they delocalize, but for relatively moderate lattice, they are still localized. So what we do? We use the interplay between gravity, spin-orbit coupling, and interactions to improve the clock. Why? Well, we were able to operate in this tilted lattice at much shallower lattice, but still prevent the undesirable motional decoherence because the Warninger-Stark states are kind of localized. But because we decrease the lattice depth, then the smaller confinement allows us to suppress detrimental P wave in elastic losses because they were happening when the lattice was very deep and the on-site density very strong. Now, because the lattice is shallower, the on-site density is lower and we don't have these bad P wave interactions. Now, and this was the magic, we had a spin orbit coupling, so we do have a little bit of we do have S wave interactions. So where we were able is to manage the interplay between S wave and P wave interactions and make them completely cancel. And this allows us to explore new fundamental limits and new type of many-body physics. So let me explain a little bit what we did. So in this vertical lattice, as I said, the atoms are localized now in harmonic oscillator levels inside the pancake, but also we are going to have a label for the lattice or the Warninger-Stark state. These are the eigenstate of the single particle Hamiltonian. So the Hamiltonian, besides having the on-site interactions between atoms in the same pancake, because of a little bit the localized nature of the Warninger-Stark states, we can have interactions between nearest neighbor sites, and the dominant ones are S-wave, because remember, because of the spin-orbit coupling, the atoms in different pancakes can have different phases. So the P-wave were what we had before. The S-wave depends on this spin-orbit coupling angle 5. We see 5 is equal to 0. There cannot be S-wave interactions. They are nearest neighbor, so they're weaker. This overlap is smaller. S-wave are stronger, but because of the atoms are more delocalized, this can become comparable. These two can become comparable. And if we compute what is the effective density shift in the Hamiltonian, we can see that we have an interplay between S-wave and P-wave, and we can use this competition to actually make this term completely vanish and cancel the density shift. And that's exactly what we did. This is the density shift versus lattice depth. At a specific lattice depth, the competition between, this is the ratio between the S wave and the P wave. When they become comparable, they can cancel each other. And we were able to measure over 10 hours and observe a fractional density shift below 10 to the minus 21 per atom. And with that, we also were able to see coherence times that were approaching 37 seconds, almost 1 minute. That was exciting because we were able to really use many-body physics trying to make a better clock, and also, well, better clock will open new opportunities on many-body physics. The interesting part is that we know, or Einstein taught us, that clocks at a different gravitational potential tick at a different rates. So for the case of Earth, the differential gravitational redshift is set by GH divided by C squared, and for the parameters of air, this means a differential frequency redshift that is of the order of 10 to the minus 19 in a millimeter, at a height of a millimeter scale. So that's really this is a small quantity in trap ions. They were able to measure a few years ago the gravitational redshift in a sample separated by 30 centimeters. But because we were able to operate the clock at this magic point, then we have been able to resolve the redshift in a millimeter scale sample. So over the course of 10 days, the experiment completed 14 measurements. For each measurement, what they measure is the differential ticking between the half of the cloud and the other part of the cloud at different heights. They were separated at a millimeter distance. And then these measurements where the differential shift was plotted. These are the points, and we have the um, the weighted mean is the black line. We have the dashed lines, solid lines that were the associated statistical uncertainty, and the expected gravitational redshift is shown in red. That is in agreement with what they measure. So they were able to measure for the first time redshift in a millimeter scale, and it was published this year in Nature. So that's a very exciting direction. So in the last part of the talk, I'm going to more talk about the other opportunities that we have to combining this type of physics now to also the other possibilities of combining with nuclear spin physics and and motion. So first, as I mentioned before, the alkaline strontium atoms, the fermionic isotope, has a nuclear spin I that is as large as 10. So in addition to the ground and excited state, we have 20 more levels to play with. But the important part is that because in these atoms, both has J equal to 0, the ground and the excited state, there is not hyperfine coupling. I dot J is equal to 0, and therefore, because the electronic spin is what participates in the collisions, and these atoms are the electronic and the nuclear spins are decoupled, there is no coupling, then this translates in the presence of an SUN symmetry in the collisions of the atoms. This SUN symmetry, that means that atoms that collide, they cannot change the internal. If you have one atom in one nuclear spin colliding with an atom in the other nuclear spin, because of this SUN symmetry in the collisions, they cannot change and scattering and generate other different nuclear spins. So there's basically the scattering parameters of the collisions are independent on what nuclear spin level you are. And this opens very interesting possibilities because SUN symmetry can have remarkable consequence in an atomic system. For example, in a quantum system, we can have SU3 symmetry, for example, in quarks, in high energy physics. Also, SUN physics, and if n is large, 1 over n can be used as an expansion parameter. SUN physics, for example, can give rise to new states of matter. Even we show that, for example, because of SUN symmetry, we can have really a new type of chiral spin liquid in as a mode insulator, and I mean with topological properties that, as recognized by the Nobel Prize in 2016, they can be very exciting. And moreover, this SUN symmetry, we show that in principle can open the possibility to build an error-free quantum computer. So I'm going here very fast. I'm just wanted to mention that we have measured this SUN symmetry in our clock. The idea that we did is that before we were only populating a single nuclear spin state. Now what we did is we opened the possibility of have different nuclear atoms, in spectator atoms, populating different nuclear spins in the ground state. And what happens is that if we are going to look at the ticking of the clock, of course, in the presence of these other atoms that are spectators, they are going to introduce a density shift again. So the density shift of the clock comes from the interrogated atoms, but also from the collisions with these other spectator atoms. But because of the SUN symmetry, the density shift only depends on the total number of spectator atoms and not how they are distributed. So they can be distributed in different ways. And as long as I have the same number of atoms, then I will have the same density shift. And this is exactly what we measure. So for example, we measure the density shift versus excitation fraction, the same plot I showed before, when we were interrogated all atoms in a given nuclear spin, but also we have other atoms in different nuclear spins, and sometimes we interrogate this nuclear spin and we get some results. Sometimes we interrogate another nuclear spin with 29% population, and as long as the population was the same, we get the same result. If we change the population of the spectator atoms and we have only 12%, we have a different result. But basically we were able to actually measure something that is consistent with SUN symmetry in the collisions, and also the slope of these different density shifts were independent of the nuclear spin that we interrogated, showing that we can have this SUN symmetry in our system. So it was interesting because when we were measuring this SUN symmetry, we got contacted by someone that at that time was writing this Big Bang series. And according to them, they were going to make a chapter when Sheldon was going to come to Gila and talk about the SUN symmetry that we measure in the clock. And then this chapter, they never came, this didn't happen, but it was fun that this paper caught attention, and they were interested in bringing Sheldon to Gila. Well, so the last part that I want to say is that, well, everything that so far I talked to you about was in this 1D lattice, but now we have been able to cool down the atoms furthermore and load them not in 1D lattice, but load them in three-dimensional optical lattices. So we have, instead, before we have a gas of microkelvin temperatures, now we have been able to create a quantum degenerate gas in a 3D lattice and reach temperatures of T over Tf of 0.1, offering the possibility to really work in the quantum regime, and we can have even enjoy 20 seconds of coherence time in this 3D lattice that is the record in 3D lattice systems. So we were able to actually further confirm the idea of SUN, and in principle, when atoms are in this lattice, they will have what we call two orbital SUN hover model description. So the atoms in the lattice can tunnel in from one side to the other, like this in the lowest band. And the ground atoms in the ground and excited state have the same tunneling rate if they feel the same lattice. But when we have two atoms in the same side, we can have different type of interactions. In this case, for example, because they're ultra cold, the P wave interaction disappears, and the only interactions can happen between atoms in the ground state with different nuclear spins. So we can have an interaction between atoms in the ground state or in the excited states, the intraorbital spin interactions. We can have interactions between the ground and the excited state. We can have the direct term or the exchange term that depends on the interaction or the scattering lengths between the Eg plus and the Eg minus, so different scattering lengths in the system. If we have SUN symmetry, all these parameters are independent of the nuclear spin and only depends on the symmetry, on the Pauli statistics of the system, if we have symmetric Eg state or antisymmetric Eg state. And in fact, that's what we measure. So we have one atom per side. This serves as a reference. But when we have 2 or 3 or 4 atoms per side, then there is the energy cost of bringing the atoms from the ground to the excited state was shifted because of the interaction energy. And we were able to see that there is only 2 peaks. So if you have 2 atoms, you have only the symmetric and the antisymmetric peak consistent with the SUN symmetry, no more peaks. Same for 3 atoms, same for 4 atoms. So we were able to, and by measuring this, we were able to recalibrate the interaction parameters of the system. Furthermore, we were able to see that if we have the pure two-body collisions in the lowest band of the lattice, we were not able to agree with the measurements that were done in the clock. You see that there were some difference, and the difference comes from the fact that the atoms can virtually populate excited bands, and this can give rise to effective multi-body interactions. So by accounting for the effective small corrections for virtual population in the excited bands, we actually were able to as a function of the lattice depth, determine what is the energy shift for 2, 3, 1 atoms accounting for these corrections because of higher band, and actually determine that in fact we have SUN symmetric collisions and SUN magnetism in our system. And just finally, to conclude, I just want to measure that in a 3D lattice, we have the flexibility also to actually control the spin-orbit coupling angle. In the case of the 1D lattice, we were able only to interrogate the atoms perpendicular to the pancakes, because otherwise, if we have the laser along the pancakes, the atoms were going to blow away. But now, if we have a 3D lattice, we can orient the orientation of the laser at a different orientation, and in principle, we can, if we allow the atoms to tunnel, for example, along the pancakes only, then we can control the degree, the projection of the wave vector along the tunneling directions. For example, if the atoms are tunneling in a pancake, in a plane, and the laser is perpendicular, then there is no spin orbit coupling angle, because it's completely perpendicular. Of if we orient the laser at a specific angles, we can have a spin orbit coupling angle that can be equal to pi. So we can control the degree of spin orbit coupling, and just by controlling the degree of spin orbit coupling and the interplay between interaction and motion, we have been able to show that we can generate, for example, spin squeeze states. We have been able that we can show you can generate super exchange interactions that are not of the form S.S, but of the form SCSC, and use this system in principle, theoretically, has predicted we can use this system to generate cluster states that could be useful for quantum computation. And also we can use this system, for example, to create CAD states. So all just what I said, that is this opening the interplay between spin orbit coupling and interactions, are opening a great path to actually explore very rich physics in many body physics in our system. And with that, I just want to conclude that there is a great vista ahead. And in principle, we should be able to, in the future, not only interrogate, get a better clock because of reducing systematics, but actually get a better clock by entangling the atoms. In principle, the interplay between spin orbit coupling and interactions might allow us to really use these systems to build gates and maybe the next generation of quantum computers. And as I mentioned, we measure the gravitational redshift in a millimeter scale. So we should be able in the future to start to look at the interplay of interactions or many body physics in a curved space, and understand a little bit more perhaps about quantum gravity. That could be very exciting. And with that, let me thank you for your attention.
Thank you, Anna, for fantastic talk. Do you have any questions? Please just go forward. Do you have? Please just go ahead.
Oh, I've got a quick one on the thing you just mentioned on the ripples of space-time. That's an interesting one. Do you know how? So you currently got millimeter resolution, but how much resolution would you need to detect gravitational waves?
Yes, it will be. I mean, the problem for actually gravitational waves, we will need to go to the 10 to the minus 21, and we have to have the clock. We have to put the clocks in space. But I mean, Jun Ye has a proposal on how to do that. So I mean, of course, it needs to be not local, but we have to separate the clocks at a different position in space. Put the plots in different satellites and coordinate the clocks so they can see what is the different frequency that they are measuring. I mean, but in principle, it could be possible. I mean, we were able to. I mean, the speed at which the precision of this clock is advising is incredible. So at the moment, we were able to suppress density shift at 10 to the minus 21. So
that's pretty cool.
Okay. Any other questions? Please just go ahead.
I have a question. Sorry.
Go.
You go first, man.
Okay, thank you. Just a quick question then. What range of interactions do you take between the atoms? Maybe you said it, I just missed it.
The interactions is of the order of few hertz. It's very small. But that's what you mean, the range or the interaction?
Atom interactions, because these could be 1 on r to the 6 or something. So there could be
interactions. We assume that a pseudo potential approximation when the interactions are really delta function interactions. They are completely contact, but they are contact in position. But when you write the Hamiltonian in momentum space, these contact interactions become all-to-all. And that's the model that we have. So that in this energy space, the interactions can be very long range. I mean, you can see that in moment, if a particle is delocalized, it in one momentum, it can collide with another atom in another momentum. Or in harmonic oscillators, if you have an atom in one harmonic oscillator, it's completely delocalized, so it can collide with an atom in another harmonic oscillator state.
But do you have a feeling on what would change if you relax this delta function condition in real space? Because
it's quite good approximated. So I mean, that's why, I mean, this is when you look at this precision, these measurements that we did for the interactions for two atoms, they assume this delta function condition, and they reproduce, I mean, the measurement, we can perfectly reproduce the measurements of the clock. So it's a very, I mean, everything is described by a scattering length. The problem is perhaps this scattering length can have some energy dependence, and kind of these corrections, these energy dependence are the corrections kind of what we saw here. Yes, so depends on the energy of the colliding particles.
Thank you.
Any other questions? Please just go ahead.
Yeah, I had a question about earlier to do with the tuning parameters and how you actually have the coupling between these states. What is the actual physical tuning parameter? I might have missed it, but what is it you physically tune to get?
Sorry, my apologies. You just were caught a little bit, at least in my. Can you repeat the question?
Damn it, my Zooms just died again.
Mitka, could you repeat the question again?
Yeah, sorry. Can you guys hear me?
Now, yes.
Yeah, sorry. The internet is super unstable and Zoom has died like 4 times since trying to ask this question. So what I was asking is, with the detuning and the coupling you have between states, how is it you actually physically adjust this detuning parameter?
It is just the frequency of the interrogate. The detuning is the frequency of the laser that we interrogate the clock respect to the transition.
So it's literally just changing the repetition rate of the laser?
Yes, the frequency of the laser, yes.
Okay.
The frequency of the, and this is controlled by, I mean, you can control it by the length of the cavity that is stabilized.
Yeah, okay, cool, thanks.
Any other questions? I have another one. So in condensed matter system, especially in condensed systems, most of the series are based on the 1/n approximation, like for heavy fermion or for condensed insulators. But in condensed matter, n is 2 or 4. So this approximation is not controllable and cannot be checked. So is it possible to create, I don't know, controllable many systems with different n?
Yes, exactly. The n is tunable by the number of nuclear spins that we prepare. I mean, SUN systems means that you conserve, I mean, if you prepare atoms in these 2 initial states, they are not going to scatter to any others. So it depends on the initial conditions. So if we can prepare SU1, SU2, SU3, and that's something that we have done. We can change the SUN symmetry from 1 to 10 and see how things change as a function of n.
So this 1/n approximations, are they accurate? So you have for n11 or 9?
In principle, well, at some point, the 1/, I mean, you have 1/10, and in principle, it starts to become much better than 1/2. So definitely, I mean, so far we have not been in a regime where we have not been able to compute. I mean, this is the next future. We can engineer a Kondo system because we can use the atoms that are in the excited state to feel a different potential than in the ground state. So the atoms in the excited state will be the magnetic moments, and the mobile atoms in the ground state will be the delocalized electrons, and they have this exchange interaction between them. So, and we can change the n and try to see when we go from SU1 to SUN. The temperature, of course, are very low, but this is in the list of things that we'd be very excited to check.
Okay, thank you. Okay, last chance for a question. If any we have, just go ahead. If not, let the speaker, let's thank the speaker again. Thank you, Anna, for fantastic talk.
Thank you. Bye-bye.
Yes, and see you everyone in a month.
Bye-bye.